Hey folks, Ms. Gosling here. In this video, you are going to learn about the implications of de Broglie's discovery of matter waves. So this video is going to look at the work of the Copenhagen team, Niels Bohr, Erwin Schrodinger, and Werner Heisenberg. And by the end of the video, you're going to be able to describe the Copenhagen interpretation. So you'll be able to explain what new science emerges from the discovery of matter waves. So our cast for this video is depicted below. We start with Niels Bohr, who you guys may remember from the Bohr model of the atom. Next, beside him, we have Mr. Werner Heisenberg, famous for Heisenberg's uncertainty principle. And beside Mr. Heisenberg, we have Mr. Erwin Schrodinger, perhaps best known for his cat. Schrodinger's cat, for those who are not aware, is a little bit of a nonsensical, it's taking the Copenhagen interpretation of matter, so quantum mechanics, to kind of an absurd level. So we're not going to be getting into Schrodinger's cat in this video, but if you're interested, you are welcome to look into it a little bit more deeply on your own. So going back to our previous video, we're going to be discussing some of the implications of matter waves to our understanding of physics in this video. And I want to start by discussing how they relate to the Bohr model of the atom. So according to the Bohr model of the atom consists of a positively charged nucleus, which I'm going to just redraw as just a circle, surrounded by electrons, which exist at specific energy levels. And these energy levels are how we connect the Bohr model of the atom to matter waves. So these energy levels are what we call stationary states. They're the places where the matter wave of my electron is a standing wave. So they're the areas where that matter wave experiences resonance. So you can see from my picture, it's a little bit hard to draw this well. What I should have is my wave form traveling around the atom such that it meets the final wave and the initial wave meet up, and you can't tell where my electron might have started. So these energy levels, it turns out, are the most likely places to find an electron in the atom because they're the most stable orbitals. Now, Niels Bohr made an assumption that those electrons would only exist ever at those states, and that they could easily travel from one state to another by absorbing or emitting a photon. A couple of things that the model doesn't describe, however, is what happens with more complicated atoms, so anything more complex than the hydrogen atom. And it also doesn't really explain why some transitions are more likely than others. So for example, why might it be more likely to go from my second state to my fourth state versus my third energy level to my fifth energy level? So the Bohr model is the beginning of when we really get into quantum mechanics, but in and of itself, the Bohr model perhaps is not quantum mechanics in and of itself. However, the questions that arise from the Bohr model of the atom is what led to our discovery of quantum mechanics. And quantum mechanics is, I think, best understood through Schrodinger's equation. And I'm sure you'll have heard of Schrodinger's equation before. Everyone likes to talk about Schrodinger. But what Schrodinger's equation does is it is a wave function, which we define by which we represent using the Greek symbol psi, psi. Looks a little bit like a trident. And that wave function is similar to our classical wave equation, but is not quite the same. It's not a derived function. Instead, we verify it using experimental results. And the wave function is not something we can really observe per se, but what's really useful about it is it tells us the probability of finding an electron at any given point in space. So what we say is that the probability of finding an electron within a given volume is going to equal that volume times the wave function squared, or more accurately, the magnitude of the wave function squared. So if my wave function at a given point is 0, that means the probability of finding my electron at that point is also 0. So what happens is that until we decide to start measuring things, that electron exists as a wave function. The wave function is always so we understand our electrons more as a probability than we do as existing in a specific point in space. When we measure it, however, what happens is that wave function is going to collapse. So the wave function is now no longer valid, and that electron is going to exist instead at that measured point in space. So what Schrodinger's equation tells us is that the act of measuring reality automatically changes what reality looks like. The act of measuring an electron changes where an electron is, because until we measure the electron exists kind of everywhere and nowhere. Well, everywhere and nowhere where the wave function is non-zero. Thus, matter and light are both waves and particles at the same time until we measure them. And then, if they're behaving like a particle, then they are a particle. And if they're behaving like a wave, then they are a wave. Thus, using Schrodinger's equation, what we can actually do is we can picture our hydrogen atom as a bunch of stationary states within kind of a bottomless well, going from an energy of negative 13.6 electron volts to an energy of 0 electron volts. And within that hydrogen atom, we have stationary states. The energies at which we get a standing wave within our box. So the energies kind of at which our the length of our wave function is equal to, results in us having a node at each side of the box. So we have, of course, our first energy state, but we also have other energy levels, like so. And so we have our n equals 1, n equals 2, and n equals 3 standing waves. And we, of course, can have more than that as well. And those are going to each correspond to my energy levels and to the solutions for Schrodinger's equation. Now, moving beyond Schrodinger, we go to Heisenberg and Heisenberg's uncertainty principle. So, as I mentioned earlier, with quantum mechanics, with quantized particles, we can really only understand them as a probability versus as a physical space until we measure them. So from that, we get Heisenberg's uncertainty principle, and that limits how precisely we can know the position and the momentum of something in the quantum mechanical realm. So we have our position and we have our momentum of a given electron. And if we look at the uncertainties in position and momentum, uncertainty, for our electron, we know that if we multiply them together, they have to be greater than or equal to Planck's constant divided by 4 pi. So what this means is that if we know the position of our electron to a very, very specific amount, so if we are completely sure what the position of the electron is, then its momentum becomes infinitely, the uncertainty in its momentum becomes infinitely large. And the opposite is also true. So the more we know about the speed of the electron, the less we know about its position, and vice versa. And the same is true about our uncertainty in energy and our uncertainty in time. So from Schrodinger and Heisenberg and Bohr, we come to the Copenhagen interpretation of physics, which we now know a little bit more as a little more commonly as quantum mechanics. And that is that nothing is real until we observe it. So our light is both a particle and a wave until we observe it acting as either a particle and a wave. An electron exists everywhere within the atom until we measure it as being at a specific energy level. The act of measuring reality changes reality. And with that, let's go ahead and talk takeaways. So our first two takeaways are the same as for the previous video. Light and matter both act as both a wave and a particle. And from that, we get the Bohr model. From that, we get Schrodinger's equation. And I always misspell Schrodinger. From that, we get the wave function. And from that, we get Heisenberg's uncertainty principle. And because of all of the implications of these models and of this science, we now know that when we cut things down to a quantum level, to the smallest possible level, nothing is real until it is observed. The act of measuring changes the measurement. With that, it is your turn to try solving some problems. Best of luck and happy solving.